Hi, welcome to Mathematics with Tom. I am Tom, and today we are going to look at the dot product, the length of a vector, and the angle between two vectors. So let's get started. The first thing I'd like to show you is what's called the dot product. So we'll start there. Dot product. And this is section 1.2 in our text. So let's start out. We need to set our stage. Our stage is this. Let V and W, let's have two vectors. They can just be in any space. So we'll just say Rn. And then we're going to say the dot product, of V and W is, and here's how we write this. So we write V, and when you're talking about vectors and a dot product, we usually try to make the dot pretty obvious. And you can never multiply, you don't multiply two column vectors. So it can't be mistaken for multiplication, but just for clarity, make sure that this is an obvious dot and doesn't look like you're multiplying V and W, so that context is kept clear. Well, here's what it means. It means that I have the vector V, so that's V1, V2, all the way down to Vn. And I want to dot that with the vector W, so W has components W1, W2, all the way down to its last component, Wn. So the dot product, what it means is this. It says that you take the first component of V and you multiply it by the first component of W. So that's V1, W1. And then you add plus V2 times W2. So V2 times W2 plus. And then you would take the third component of V and you'd multiply it with the third component of W, and you would then add. And you continue multiplying component-wise, adding until you get to the last one, until you get to your last component, Vn times Wn. And that's the dot product.
Sorry.
It's okay. So the next thing is length. Let's find the length. Of we've used V and W. Let's take the length of X, and for simplicity, let's just look at it in R2. And I'm doing that because it's easiest to draw, and you will immediately recognize this, but the extension holds through Rn. So if I have a vector X, and I draw it, let's draw the vector X. So in R2, we have an x-axis and a y-axis, and here's my vector x. Now, if I wanted to find the length of x, well, what I would do is look at the length of each side of the triangle. Well, this is the coordinate x1, and this is the coordinate x2. So the sides of x are x1, or of the sides of this triangle are x1 and x2. And you probably are already ahead of me. In other words, we just use the Pythagorean theorem to find the length of x. And here's what we do. We say the length of any vector, but in this case x, of x is denoted is denoted as the length of x. Okay? So let's calculate that. And what do we get? So, well, the Pythagorean theorem says that the hypotenuse squared, well, that's the length of x squared. That's the length of x squared. Is equal to the sum of the square of the legs. Well, that's x1 squared plus, that's also x2 squared. Now, I'm out of board space here, so I'm going to move this up over here. Let's come up, let's take this here. And my next step says that the length of x squared is equal to, it's so easy to overlook subtleties. And what does it mean if x1 is squared? It means that it is x1 times x1 plus, it also means that x2 squared means that you're taking x2 and you're multiplying it by x2. Well, wait a minute, look at what we have. This is the first component of x. This is also the first component of x, plus second component of x, and the second component of x. That's right here. First component of x times the first component of another x, plus second component of x times the second component of x. Let's write that. This is x1, x2, the vector x dotted with x1, x2. We're just using the definition that we first created right here. And now our vector is only just two components. So this just says that the length of x is very simply x. The length of x squared is x dotted with x. Okay. Now, if you wanted the actual length of x, you would take the square root. So you could also say, if you needed to, that the length of x is equal to the square root of x dotted with itself. Okay. So let's try this not just with x. Well, notice this. This whole problem started with a right triangle. That's how we were able to find the length of x. Let's try this again. But we're going to change this a bit. Let's do this. Now, I've used v and w over there, so I'm going to use a v prime. How about let v prime and w prime be vectors in, how about R3? Oh, and let me go back one thing. So the length, I'll write it here. The length of any vector squared is equal to the vector dotted with itself. This was an example that we showed you for R2, but it does extend into for a vector in any dimension. Okay? Let's try this one more time. Let v prime and w prime be in R3 and be perpendicular to each other. Perpendicular to each other. And also for the future use, but when I see perpendicular, that's a long word to write, so we're just going to use this upside down T from now on for perpendicular. All right, what does that look like? That would mean that I have some vector like this, maybe like that. That would be v prime, And then I have a perpendicular vector. Hopefully I draw a perfect that. That would be my W prime. And we know that they're perpendicular. In other words, they form a 90-degree angle. Well, what does that mean? That means that we can use, to talk about this, we can use the Pythagorean Theorem. So, well, let's do that. And let's see what happens then in this case. Let's just apply the Pythagorean Theorem. Well, in order to do that, we need this side. What is this side? Well, let's take before that, we have the length of this side is just the length of W prime. Oops, sorry. It's the length of W prime. This, we need the length of this leg. Well, that's just the length of V prime. So my question to you is, what do we know about this vector? Well, that came from when we first discovered linear combinations. This is the vector of W prime minus V prime if I draw it like this. And we just need to work with its length. And there we go. Now let's apply the Pythagorean Theorem. So, what do we do? Well, that says then that the length of W prime minus V prime squared is equal to the length of W prime squared plus the length of V prime squared. Oh, but now let's use this is hard to work with. So let's change the form to our newly discovered tool. Our newly discovered tool says that the length squared is equal to the dot product of a vector with itself. So this becomes W prime minus V prime dotted with W prime minus V prime. W prime, the length squared, well, that's W prime dotted with W prime plus V prime dotted with V prime. Now, your homework assignment, this is, we're not going to do this here, this is a wonderful homework practice, is to show, that the left-hand side, W prime minus V prime, dotted with W prime minus V prime, that it actually distributes like you would expect. If that was a multiplication sign, your result of this is W prime dotted with W prime minus 2W prime dotted with V prime plus V prime dotted with V prime. That's your homework assignment, and we're going to use that. So, let's write that again. I have W prime dotted with W prime minus 2W prime dotted with V prime plus V prime dotted with V prime is equal to W prime dotted with W prime plus V prime dotted with V prime. Oh wow, look at this. Look at what happened. If you look at this, here's a W prime dotted with a W prime, but here's one also. Those cancel. Here's a V prime dotted with a V prime. Here is one on the other side. Those also cancel. So what am I left with? This simplifies to minus 2 W prime dot V prime is equal to 0. Let's just divide both sides by negative 2, and I'm left with that W prime dotted with V prime equals did we just discover? Well, let's look back to where we started. What did we say about v prime and w prime? We said that they're perpendicular to each other. So what have we just shown? We've just shown that if you have perpendicular vectors and you take their dot product, the result is always 0. We did it for R3, this is true for Rn, but that's the important takeaway from this. And that is this. Perpendicular vectors, oops. I said I wouldn't write it again, and here I am writing it, maybe just because it's so important. But this time I'm using my symbol. Perpendicular vectors have 0 dot product. Okay. We're going to stop there with the dot product. And in our next video, we're going to ask the question is, how does the dot product help us when, in fact, they're not perpendicular vectors? Thanks for watching, and see you in the next video.